Okay, back to the material. Where we are? We are in the process of discussing magnetic force, right? So we introduce magnetic force acting on a point charge. Again, you remember, if a point charge flies, only then it experiences magnetic force, right? And if you have a wire, right, wire exposed to the magnetic field, of course, it will also experience a magnetic force. And we introduce those two formulas, right? Okay, so now let's continue playing with those formulas, right? So let's this time solve this problem. It's not from this book. I took it from Giancoli, sort of classic book in physics, right? All right, and what do we have here? We have infinitely long straight wire, right? So it goes from that infinity, it starts at that infinity and goes to that infinity, basically. And current I, 3.5 amps. Okay, first object in the system. Second, rectangular loop with a current. Current I1. So here we have I, here I1. So we need to distinguish these two currents, right? And although the values of these currents are the same, you see I1 equals to 3.5 amps. But of course, I need to use subscript so that we would know which current we're working with, right? And we're using. Right, okay, so that's the electrical part. Now some geometry is given. Of course, the size of this loop. So width or the length, whatever, A, 10 centimeters. But immediately I converted to meters, 0.1 meters. Then height, 5 centimeters, 0.05 meters. And then the distance from the wire to the upper part of the loop is D. Okay, I didn't have enough space, so I wrote D is 3 centimeters or 3 times 10 to the power of minus 2 meters. Okay, so that's the system. And now what's the question? The question is, we need to find the net force. Okay, of course, it will be a magnetic force, right? Acting on the loop. Of course, this object and this object, they're going to interact. The wire is going to exert force on the loop. The loop will exert force on the wire. But the question is, of course, those forces in absolute value are going to be the same, right? According to the Newton's third law, but of course opposite in the directions. Right? But here the question asks, okay, the problem asks, what will be the force on the loop, on the rectangular loop? Right? So this problem sort of ideologically very similar to the problems which we discussed in the previous recitation class. You remember we had first two wires, right? And we found the force acting on one of those wires, right? And you remember how we treated those problems. Object, a wire, which experienced a force. It was, okay, just an object, the object, right? And the second wire was this or a source of the magnetic field, right? So one object was the object, right, on which force was exerted. And the second object was the source of the magnetic field. Then we had 3 wires, right? You remember? We had 3 wires, and we need to find force on one of those. In this case, these 2, for example, wires were the sources of the magnetic fields, and these experienced the force. Now, the same story. One object will be, in this case, is the source of the magnetic field, and the other object is the object. Right? So in this case, wire, infinitely long straight wire, is the source of the magnetic field, and this loop experiences magnetic force, right? So now, and after this, sort of identifying how we're going to treat, figuring out how we're going to treat these objects, now we can start looking into details, All right, so let me write first Probably, okay, treat the wire as a source of magnetic field. Treat the wire, this infinitely long straight wire, as a source of a magnetic field, right? And can we write the expression for the magnetic field strength? Of course, at this point, everyone can easily write it down, right? Because we've derived that formula and we used it so many times. B equals mu naught times I, this I, right? Because this is the current flowing through this wire. And divided by 2 pi and perpendicular distance from the wire to the point where you want to know magnetic field. So that's the expression. Now, but of course, we will need to also need to know a direction of this magnetic field, because that is the magnitude, strength, right? So direction, easy. Right-hand rule number 2, you remember, outstretch your thumb in the direction of the current, and your curled fingers gives you a direction of the magnetic field lines. And of course, we remember that magnetic field lines of an infinitely straight wire are circles, right? Circles centered on the wire. So in this case, outstretch my thumb, curl my fingers. So above magnetic field will be out of the page, right? And here into the page. Okay, so now let me draw this. So here I set into the page. So we're going to have crosses. Right, so I will draw something like this. So that's B. And of course, above, as I said, out, dots. So that's magnetic field created by the wire. Okay, let me write direction. See the figure. Okay, so now we know the magnetic field. As a result, it means that we can forget about this wire. So these green crosses or dots, that's what we need now. Right, so now next. So this loop now is exposed to the magnetic field. And we need to find the net force. So we know the formula for what? For a piece of wire with a current. If you have a piece of wire of length L, and if it's exposed to the magnetic field, we can, in the previous class, in the previous recitation class, we practiced how to find the magnetic force. You remember it was I, the value of the current, L cross B, right? So we know the formula for a straight piece of wire. Here we have our loop consists of 4 straight pieces, right? This, and this. Maybe I can label them. Right? So let's say this is piece number 1. I think, let me look which way I label. Yeah, this will be piece number 2. This is 3, and this is 4. Right? So it makes sense to divide this loop into 4 straight parts, in this 4 straight pieces, right? And as a result, we can find the force on this separately, on this, and that, and then we can just add them up, forces, right? Add forces up in order to find the net force acting on the loop, right? So, okay, let me write. Divide the loop, right? And as a result, we can write, so F net force, F net, equals to, of course, force on the first wire plus force on the second piece of the loop, this one vertical, plus F3 and plus F4. step by step, right, getting deeper. First, we identify the magnetic force, the magnetic field. Now, split the loop into 4 parts. And now we just need to take care of these forces separately, one by one, right? So first, let's see directions of these. No, let me write first the expression for the magnetic force. So F equals I L cross B. You remember in the previous recitation class, we practiced this formula, right? So direction of the force, maybe I can should frame this because this is just a formula which give us magnetic force acting on the current of length L, where there is a current I, and which is exposed to this magnetic field B. Okay, so let's find directions of these forces, F1, F2, F3, and 4. And then, of course, I will start writing magnitude, the magnitude of these Fs, all these Fs, right? So let's first take care of the direction. And of course, direction of force is determined by what? Cross product, L cross B. And again, you remember, what determines direction of L? Direction of the current. Direction of the current gives us direction of L. That's how we introduce L in this formula, right? Okay, all right, so now let's see. F1, so force acting on the top piece of this loop. Direction of L, again, determined by direction of the current. In this case, current I1. Probably I should add the subscript here to avoid confusion. Because, okay, right now I wrote just formula in general. But I think it makes sense to avoid confusion, right? So to put the subscript I1, right? Because here, current I, this current has nothing to do with this current, right? So current I is in this B, right? So let me put a subscript 1, right? Okay. So L, determined by the direction of current. Current flows this way in the first part, right? Current that way. So L is that way. Magnetic field is into the board. So right-hand rule number 1, how to find direction of the cross product. First, align your hand along the direction of L, that way, right? And then cross it with B. B is into the board, so I have to position my hand like this in order to curl my fingers in the direction of the magnetic field, right? So, you see? As a result, magnetic force is straight up. So that will be the direction of the force F1, right? Okay, let's do the same for all these 4 wires, pieces of wires, right? Pieces of loops, and then magnitudes. Now, F2, acting on this part, from this corner to that corner. So now L, direction of L determined by the direction of the current, and current is straight down. So, in magnetic field, still into the board. So, right-hand rule number 2, first align your hand along L, sort of like this down. And I have to position my hand like this so that I can bend my fingers in the direction of B, right? So you see, B is into the board, so I have to position my hand, right hand like this. And you see, as a result, my thumb gives me direction of the magnetic force. So magnetic force acts that way, right? I hope at this point you are comfortable with applying right-hand rule. If not, okay, tell me and we will practice more during office hours. All right, so this will be, because from now on, almost every class we're going to use right-hand rule number 1. So that's F2. Now F3, exactly the same story. L cross B. Now current that way. So it means that L also that way, but B is still into the board. So I have to apply right-hand rule. L cross B, right? As a result, my thumb gives me a direction of the magnetic force. So it will be straight down. So F3. In the last, these F4. Now L is up because current is up. Magnetic field is still into the board, so L cross B. So you see L cross B. As a result, magnetic force is to my left. So that's F4, right? Okay, so these are directions. Now, what can you say about force F2 and F4? F2 and F4. They have the same length, right? Right. Exposed basically to the same magnetic field because they are at the same distance from the source of the magnetic field, right? And the same current flows through this wire and through that wire. So, what can you say about their strength F2 and F4? Yeah, F2 and F4, they're the same in magnitude, right? They're the same in magnitude, but opposite in directions. So if we assume that loop is kind of sturdy, right, it's impossible to distort like this loop, for example, right? But of course, this is the rectangular loop. So in that case, these two forces just cancel each other out, right? Without contributing anything to the net magnetic force, right? So F2, let me write. So F2 absolute value equals to F4, right? But opposite in directions. So they cancel each other. Oops. They cancel each other. So from our this expression for the net magnetic force, I can cancel this and this. Okay, less work to do. So it means that we need to find only F1 and F3. Okay, less amount of work. Can you tell me quickly, which force is going to be stronger, F1 or F1 or F3? I think it should be obvious for you, right? Because, okay, length is the same of this wire and that wire. Current length is the same. Current is also the same. But magnetic field, of course, different. Since this top wire is closer to the source of the magnetic field, of course, magnetic field over here will be stronger. And as a result, magnetic force F1 is going to be stronger than the magnetic force F3. As a result, the net force on the loop will be up, right? So basically now we can tell what will be a direction of the net magnetic force, right? Sort of conceptually. But no, now let's get to details and find the magnitude of F1 and F3. All right, so let's start with, so this, we took care of these two forces. Now F1. F1, let me write it first in the vector form. I1 L cross B. Right. And as I said, magnitude. Right, so magnitude of F1. And okay, let me write it in this way. First, let me write down the magnitude. So it's I1 L and L B and sine of angle. What is the angle between L and B? L, direction of current that way, B, straight into the board. So the angle between them is 90 degrees, right? So L and B, so 90 degrees. Sine of 90 degrees, right? So in the right-hand rule number 1, right? So that's what I want to find. This is 1 sine of 90 degrees, right? So I just need to, and what's the value of L? the value of L, it's A, right? So that's the width of the loop. So this is A, right? So absolute value is I1, A, B. I1, A, and B. B, it's this B, right? This is the formula. So it will be I1A, and instead of B, I will write mu naught times I of A. Now it's I, and divided by 2 pi. Which distance? Carefully. 2 pi. R here I wrote in general, right, for which can be used for any piece of the loop. But now we have to be careful. I'm talking about this wire, this piece of the loop, right? So which is at the distance d from the source of the magnetic field, right? So here I will have to use mu naught I divided by 2 pi d because we want to find the force on this top part of the loop. Right. Okay, so here, of course, 2 pi d. Right. Okay, so basically now let me just make it look nicer. All right, so F1 will be equal mu naught I1 divided by 2 pi d and times A. Right. So that's the formula for the magnitude of the force F1. Right. Okay, let me frame it a little bit. Okay, so that's the first part. Now let's do the same for F3. So absolute value of F3. Again, it will be I1 L. And again, L equals to A, right? Then B and sine of 90 degrees. Of course, the value of B will be different, but angle is still 90 degrees, right? Because again, L that way, magnetic field is into the board, so angle between these two vectors are 90 degrees. So it will be, all right, I1, then times A, B, and again, sine of 90 degrees. But now, of course, B is I1A. And instead of B, I will write the same, but now mu naught I divided by 2 pi. R in that case, it will be D plus B, because at the bottom of this loop is at the distance D plus B. D plus B. So I will write here mu naught times I divided by 2 pi D plus B. Right. Almost done. Okay, so direction we see already, right? So I can write it here. Direction, it's what? Here it's up. Direction of this force, of course, down. We just analyzed it a few minutes ago. Okay, so final stretch. So let me write F net. And you see, I'm not writing a vector sign on top, right? Because now I want to find the absolute value of the net magnetic force, right? Because we know that F1 is up, F3 is down, and of course F1 is going to be largest, so the direction of the net magnetic force is going to be up, right? So now let me take care of the absolute value. So it will be, which way actually I wrote it? No, I just, yeah. And I will write at the end. So it will be F1 minus F3. Again, as I said, because F1 is up, F3 is down. Right. Again, let me emphasize. So this is up, and because this is down, so that's why I put minus between them. Okay, and so that's F1. This is F3. So it will be mu naught I1 times A divided by 2 pi D. So that's what this is. Then minus F3 mu naught I1 again times A divided by 2 pi and D plus B. Okay, we can make it look a little bit nicer. We can factor out. Actually, plenty of can be factored out. So let me do that. F net will be equal to mu naught I. Okay, let me first write without the subscript I, and then I1 times A divided by 2 pi and 1 over D minus 1 over D plus B. And obviously F1 is larger than F3 because look, it's 1 over D and here 1 over D plus B. So of course this is D plus B is larger, but because D plus B is in the denominator, so this is smaller than that, right? So we're going to get absolute positive value. It means that up. Right, so and let me write endpoint upward. Okay, so if you plug numbers, I'm not going to do it. Right. So everything I converted into meters already. And F net equals to 5.1 times 10 to the power minus 6 newtons. It's just a force, right? Magnetic force, so units of newtons. And direction upward, or we can write towards the wire. Okay, so again, major steps. First, you need to identify which object is going to experience the force, which object is the source of the magnetic field. So source, object. Then we divided the object, the loop into 4 parts, found the directions of the forces. Immediately we found that this and that cancel each other. And then found the absolute values of F1 and F3. And subtracted them because we see that they obviously act in the opposite directions, right? So that's the problem. It's nice. It's not significantly more complicated than the previous, but of course longer because now we have to apply some logic, right? So analyzing this situation. So that's why I took it borrowed from Jan Colley's book. It's not from this book. Okay, so if you have questions, concerns, you can say something, scream something. If not, then we will move into stuff which I usually discuss in the lecture. But again, because of the holiday on Wednesday, so we have to discuss it in our recitation classes. Okay. So then I will start erasing because now I will need plenty of whiteboard. Okay. So now let's go back. So here we discussed the magnetic force acting on the wire of length L. Now let's go back to a point particle, electrons, protons exposed to the magnetic fields, and we will analyze motion of particles in the magnetic field in special situations. Right. We started discussing that in our lecture, but we haven't finished. I just barely started. You remember? I called a certain motion as a cyclotron motion, right? So that's what we need to continue discussing today. Okay, probably I will write cyclotron motion. Cyclotron motion. Right. Okay, so let's start first with this situation. What if you have, for example, a magnetic field pointing this way? Oops. So B. Right. And what if I take, for example, an electron or proton and send it along the magnetic field lines? So let's say charge Q, and it flies this way, V. And of course, okay, let me write down, of course, the force which we have to use are Q, V cross B. Universal, fundamental formula which allows us to calculate force which a charge experiences if it's exposed to a magnetic field. Right? Let me frame it. Right. And so in this case, what will be the value of the force? Since V is parallel to B, the angle between them is 0. Sine of 0 degrees 0. Cross product is 0. In this case, magnetic force is 0. In this case, particle is not going to experience the force. It means that it will fly straight with the same velocity forever and ever. Right? So in this case, F equals 0, magnetic force, right? And as a result, we have uniform translational motion. Uniform translational motion along the same line with the same speed forever and ever, right? So as a result, we have a uniform translational motion. So it's a boring case, nothing interesting over here. So, but we need to mention it. So now let's move to the next situation. I just separated this first case. Now let's send a particle perpendicular to the magnetic field. Right? So now let's say magnetic field is into the board. Yeah, maybe I will add additional line of, so these are magnetic field lines showing our magnetic field. And now let's assume that we have some particle, charged particle Q, which flies with velocity V. And now we want to discuss this motion, right? So first of all, in order to understand what happens with this particle, of course, we need to realize what happens to the the force, right, acting on this particle. Of course, if no force acted on the particle, this particle would fly straight, like in this case. But in this case, force is not 0. QVB, right? So now V and B are not parallel to each other, they're perpendicular. The angle between V and B is 90. Okay, guys, somebody's mic is on. Whose mic is on? Let me mute. Okay, sorry, I had to mute. Right, okay, so in this case, force is not 0. What's the direction of the force? V cross B. V that way. B is into the board, so I have to curl my fingers like this, right? So you see, V cross B. As a result, magnetic force acts this way. We assume the charge is positive, for example, for simplicity. Let's assume charge is positive. So in this case, force acts this way. So that's direction of the force. It's perpendicular to the direction of motion, perpendicular to the velocity. It means what? Which trajectory we're going to get if force is perpendicular to the velocity. This force cannot change the magnitude of that velocity. So speed is going to be the same. It means we're going to have, again, here, uniform motion, but not translational. No way. So in that case, what does this force do if it doesn't change speed of the particle? It changes direction of that velocity. So first particle tries to fly this way, then this way, this way, this way, this way, this, and eventually it gives us circular orbit. When the force acts perpendicular to the direction of motion all the time, you see, force is perpendicular to the v, because you remember cross product. The direction of the cross product perpendicular to both of these vectors, v and b. So force all the time perpendicular to v. It all the time keeps, force all the time keeps changing direction of the velocity. As a result, we're going to get circular orbit. Let me draw it. I've been using a plate, right? It's kind of dirty with markers, right? I have to use something. What is available? Right. So let me draw a nice circle. I hope nice. Okay, it should be good. Okay, decent, right? So that's the trajectory, and this is the center, right? And as I said, all the time, force is perpendicular. If, for example, let's imagine that the particle is here. So this is direction of the velocity, but direction of the force still perpendicular, right? So it will be this way. So still force. If particle is here, again, force will be perpendicular, F, right? And velocity is this way. So this is the cyclotron motion. This circular orbit called cyclotron motion, right? So let me check if I mention. Yeah, okay, so now next, let's describe this trajectory. So what does it mean describing a trajectory, this trajectory? It's a circle. If you know the radius of this circle, you know everything about this trajectory. So let's find the circle, the radius of this cyclotron motion. Cyclotron radius. Let's find cyclotron radius. Right? Okay, in order to do that, let me separate this part deeper. Okay. And in order to describe circular motion, you remember in Physics 1, which coordinate system did you use in a previous semester or maybe earlier when you remember when you analyzed motion of satellites, for example? Now some object attached to the rope and you spin that rope, that object. Every time you use two coordinate axis along tangential direction and radial direction. Let's do the same here. So let me choose coordinates. This is R towards the center, right? And T tangential. How should I draw it? So that is tangential direction, T. So instead of X and Y in Physics 1, we decided to use R and T. They're still mutually perpendicular to each other. So we can use all those beautiful features of rectangular coordinate system. But now it's more convenient to align them like this. R towards the center and T tangential, right? Okay, and now in order to describe any motion, what can be used? Universal law, Newton's second law. Let's apply Newton's second law for both of these directions, for R and T, like we've done many times again in Physics 1. But you know what? Before I start applying Newton's second law, let me write explicitly force. And also tell just basically write direction and magnitude of the force. Right? So before we start applying Newton's second law, So force is over there. So direction of F radial, so in plus R direction, and magnitude of F, of course it will be V and B perpendicular to each other, because that's the situation we decided to analyze. B is into the board, V you see this way, so every time they are perpendicular to each other. So as a result, magnetic force will be QVB, because the angle between them is 90 degrees. Okay, let me emphasize on that. Theta is 90 degrees. Okay, so now we know all the information about the force, and now let's apply Newton's second law. Let's start with the t direction. Right, so now let's apply Newton's second law in t and r directions. So let's start with T1. So force, what's the force in the, what's the value of the force in T direction? T direction that way, force is perpendicular. So force is 0, right? Because there is no force acting in tangential direction. We have only one force, magnetic, and that has a radial direction. Right? So force equals 0. As a result, Newton's second law, m times tangential acceleration equals to 0, because the force equals 0. So tangential acceleration is 0. It means that speed of the particle is the same. Uniform motion, like what we discussed conceptually a few minutes ago. Sorry. All right, so speed is constant. So we have uniform motion. We discussed that conceptually, and now we're sort of getting it from the Newton's second law. So now let's do the same for the r direction. All right, so now force in the radial direction equals to mass times acceleration in the radial direction. Which acceleration do we have here? A sub r. Again, it's physics 1. When you analyze the motion of satellites around the Earth, you remember that acceleration which we use? It's called centripetal acceleration, right? Usually students remember name, but most of the time they don't remember the expression for the centripetal acceleration. It's a square of the velocity divided by the radius. Right. So this, okay, let me use something else. So this is v squared over r. Centripetal acceleration. And of course force in the radial direction, it's our magnetic force, QVB. So this is QVB. Okay, so now let's write that down. So it will be QV times B equals mv squared over r. Just application of Newton's second law, nothing else. Again, one velocity can be cancelled. V and this V can be cancelled. And as a result, we can solve it for r. And since it will be radius of our cyclotron motion, let's add subscript cyclotron as CYC cyclotron. So it will be mv divided by qb. mv divided by q times the value of the magnetic field. So that's the cyclotron radius. So let me write it down. So it's a cyclotron radius. A few times I give a problem about this on the exam, final exam, of course, right? And on the formula sheet, I never give this formula. Every time I expect that students are capable just using Newton's second law in the radial direction, in this case, force, magnetic force, in this case, mass times centripetal acceleration, and I expect that students should be able to do this one-line derivation to get the expression for the cyclotron radius. But of course, now you have everything available to you during the exam, right? So, mv divided by charge times magnetic field, right? Okay, now before, okay, we're getting closer to the end of the class, right? So now, before we go, let's now answer one question and derive the formula. Is this motion, is it a periodic motion? Of course it does, right? It is a periodic motion. So this particle is going to circle, right, as many times as you have time. Right? So now, of course, logical question, what is a period of this motion? Let me put a new bullet, right? So the period. What is period meaning of period, right? Period is just time. It's just time for a particle, in this case for a charged particle, to complete one oscillation, to complete this one circle. It's just time to travel over this distance, which is equal to circumference of this loop, right? And you know what, on the exams, so on the tests, quizzes, right? So I notice whenever I ask about the period of this motion, lots of students, I know 50–60% of students, they just panic because it's not a motion along a straight line, it's kind of circular motion, and they overcomplicate the situation. So the answer for this question is quite simple, and everyone who is in this class, right, behind the screen, knows the answer, but maybe you're not realizing this. What's the logic? Logic is very simple to answer this question. Look, let's start with a simple situation. Let's assume that we have a straight trajectory, straight line. Some bug travels along a straight line. And let's assume that this bug travels with a constant speed. Let me, one additional minute. With a constant speed. Let's assume that we know the distance. We know this constant speed. How can we find travel time? The question is banal. It's kind of insulting for students of your level, right? Of course, you just take the distance and divide it by the speed. That will be the travel time, right? Of course, everyone knows that. Now, what if I bend my trajectory slightly and still assume the same thing? I know the distance, and I know that the bug travels with the constant speed, uniform motion, right? So still constant speed, like 5 meters per second. So what will be the travel time? Exactly the same. Take the total distance divided by the travel time. The key word, because it travels with a constant speed. And if I keep bending my ruler, and eventually let's assume I manage to bend into a circle. And the same. So let's assume that we know the distance, and we know that the bug travels with a constant speed. We have uniform motion, constant speed. What will be the travel time around one circle? The same, the total distance, which is 2 pi r, divided by the speed. And we do have uniform motion. The speed is constant. Here, from the tangential direction, we found that speed of this particle is constant. We have uniform motion. And then we added circular, so it's a uniform circular motion. So how can we find the travel time over one circle? Distance, which is circumference, 2 pi r, this, and divided by this speed. All right? So it's trivial. The question is trivial, but again, I noticed every semester I know more than 50% student at this point, if I ask a question like this on the exam, they just write a bunch of rubbish. Although I know that everyone knows the answer, right? Okay, so in this case, t equals, it's just a 2 pi r cyclotron divided by this speed. Okay, so now let's plug our cyclotron radius and we'll call it a day. 2 pi over v and cyclotron radius mv divided by qb. You see what happens with velocity, speed, it gets cancelled. Speed basically is the magnitude of velocity. So it will be equal 2 pi times mass of the particle divided by charge times the magnetic field. And then, of course, you can easily also find the frequency. For example, it's a reciprocal of t. Okay, so at this point, let's stop. All right, and next class, I didn't rush today because I knew that we have extra class relative to other sections. So I'm trying to stretch this material into 2 recitation classes. So next class, we will just look at one problem and maybe we will look at some applications of this. Okay, guys. So we'll continue tomorrow, actually. Tomorrow is the Monday schedule. Don't forget, right? Okay, guys. If you have questions, ask. Otherwise, I'll see you tomorrow at exactly the same time. Don't forget, tomorrow is Monday schedule.
Higher in the sky, the Olympic flame glows like the sun. Watching